let us start. What is the problem about oxygen and silver? Well, it is not the financial one, because even if you had 100 ppm of oxygen in a silver bar, that would only be £1 value, maybe less after Brexit, but it's not a lot. It's 0.01% of the value. So that's not the problem. The problem is that oxygen is readily soluble in molten silver. So, question, how much gas, how much oxygen can you get out of a large silver bar, weighs 1,000 ounces, it's about 3 litres volume. How much oxygen can you get out of that if you just allow all the thermodynamically equilibrium amount of oxygen to be absorbed? 5, 10, 20, 40, 60 litres? What do you think? Who thinks it's 60 litres? No one? Because that's the answer. 60 litres. It's amazing. I had to look at this very carefully. That's a slight cheat, because that's under a full atmosphere pressure of oxygen, and we've only got 20% oxygen in the atmosphere. However, that is the issue. And what is the challenge? The challenge, because it's very soluble in molten silver, but it is not soluble at all in solid silver, or almost not soluble at all. And it can therefore spoil the appearance of nice silver good delivery bars. I wanted to have a video. I couldn't find one. Next time I will have one. This is what you get. There's these nice kind of mini Christmas trees appearing as the bar solidifies. So that is the challenge. So when we were discussing this in the referees group, discussing the conference, someone said to me, "Stewart, didn't you used to work in the copper industry?" Yes. Well, aren't there some lessons in the copper industry, something about poling of copper to get rid of oxygen? Maybe there are some lessons there. Yes, I said, copper poling is a fantastic thing. You don't get it nowadays. These are large green wood poles, so wet, basically wet wood poles that used to be pushed into the molten copper bath. And the formula, very scientific, wood plus heat equals carbon monoxide and hydrogen. That's the first part of the reaction. The second part at the bottom, oxygen, either in solution or as copper oxide, plus the aforementioned gases gives CO2 and H2O and copper. So, great, we thought. So I will try to find a speaker from one of the several good delivery silver refiners who also refine large amounts of copper, talk about similarities and differences between copper and silver as far as oxygen is concerned, maybe even talk about gold. I went out and spoke to several and came back and they all said no. So that's why I am here, because basically I really know nothing about this subject. And that's in spite of having done a PhD on hydrogen in titanium, which is also a gas and a metal, but that's totally different. So I began, I did this little survey. Some of you may have seen my questionnaire. I asked a number of questions about the raw materials that were used, the melting furnace, things like flame polishing, how do you stop absorption of oxygen into silver, etc. And I found, and we'll quickly look at the results at the end of this presentation, and these are already on the website, there were many similarities in what people do, but some interesting differences. Anyway, because I haven't really got much to say, I thought I would have a light-hearted approach, and instead of just talking about the science, which, as I say, I don't know about, we'll have a cosmological digression and look at the origins of oxygen, because this really is interesting, even if it's not the subject of this conference. And then I'll talk basically about a very small amount of physical chemistry. It's like first year high school. It's the only bit I understand nowadays. We'll talk about why oxygen counts as silver, analysis, although Contant is the one that's really going to talk about analysis. And then talk about the strategies to avoid the problem, as revealed by that. So here it is. Here's the Milky Way. Here's our galaxy. Don't ask me how, but people have found out what the matter, forgetting the dark matter, the actual matter, the atoms in the whole of the galaxy are. What are they? 75% hydrogen, 23% helium. That only leaves 2%. And 1% of that is oxygen. I think that's amazing. And 1% for everything else. Wow, I thought. Why is this? It's because when stars die, when they're cooling down, they start to form other elements. And they do that by helium nuclei, otherwise known as alpha particles, combining together. They form beryllium, more alpha particles, forms carbon. Then you get carbon with another alpha particle, and it gives you oxygen. 8 neutrons, 8 protons. And it so happens that's really stable. And that's why there's so much oxygen in the universe. However, oxygen is not chemically stable because, forgive the very 19th century approach to atomic structure, it's got an outer orbital with only 6 electrons, and it wants 8. So to get 8, it's got to either borrow them from metals, for instance, or from other oxygen atoms, which is why we get the oxygen molecule as shown here. So, what about the solar system? Well, even in the solar system, you can just about see in the bottom chart, hydrogen and helium, this is not the sun, this is the planets, are totally dominant. That's because the center of Jupiter, for instance, is basically made of hydrogen. It's solid hydrogen, supposedly. It's mind-boggling. Now, oxygen is shown here. It's still high. This is a logarithmic chart. So the 2 units on the side of the chart represent a factor of 100. So oxygen is still way out after hydrogen and helium in the solar system. When it comes to the Earth is a distilled planet. We're a very small planet. We're near the sun. We've lost a lot of these light elements. There's hardly any hydrogen and carbon and so on here. But oxygen, 30% of the Earth is oxygen, 30% iron, and the rest is basically silicon and magnesium, plus a few others like gold and silver. When it comes to the crust, that's the kind of slag layer when the Earth solidified, 46% oxygen. When I told my son this, he couldn't believe it. But apparently it's true. And of course it's combined with silicon, with magnesium, with iron, etc. Now we come to the really interesting bit, the great oxygenation, how we got oxygen in the air. And it happened about 4 billion years ago. Our original ancestor was a bacterium which sat in the water, and there was no air, but it sat in the water and it absorbed energy from the sun and it excreted oxygen. And that oxygen was immediately snapped up by all the ferrous ions in the water, and it deposited in the bottom of the ocean as these banded ironstones. And that went on for 2 billion years. 2 billion years. Then all the iron in the water was used up, and the age of iron ore formation ended, the air age began, and that's when silver could start absorbing oxygen. So the message from silver is, I want electrons. Metals say, I've got excess electrons, they combine together, and some of them are more stable than others. And what we have in metallurgy is a thing called the Ellingham diagram. Don't need to look at this too closely. The interesting bits are the very stable oxides, like magnesium oxide, titanium oxide, are at the bottom. And if you're at the bottom of this diagram, you are very, very stable. What is at the top? Silver oxide, that little line at the top. And if you could look at it in detail, it would tell you above 200 degrees C, silver oxide dissociates. So it's very unstable, it hardly exists. But of course, it does exist in silver oxide batteries, very importantly. So the oxygen solubility in silver, it's defined by Sievert's law. Sievert's law tells you that the solubility, this is in molten silver, is proportional to the square root of the partial pressure of oxygen. In solid silver, the studies suggest that it is almost zero, near enough zero, but it may be present, and this is, I think, where Kongtan's analysis will show, it may be present in what's called supersaturated solution, possibly even as tiny particles at room temperature of silver oxide. And these are the solubilities there are the equilibrium solubilities under 1 atmosphere. So you can see for molten silver, above 950, you've got a lot, 3,000 parts per million. By the way, that's much less than you get in copper. But solid silver is pretty insignificant, below 300 degrees centigrade. Kongtan may tell us something different. Now, the last thing I just want to look at is the results of the survey that I did. I think maybe the two most interesting things that came out of it is that although almost everyone uses carbon in one form or another on the surface of their molten silver to prevent oxygen being absorbed, some people actually actively try to remove it. This is like a kind of silver poling rather than copper poling, using carbon rods, stirring them, and that supposedly makes a difference. One other thing is that some refiners use nitrogen, and nitrogen purges the oxygen out effectively by reducing the partial pressure. And so it is possible to get good silver bars without these needles that we saw earlier if you have the right practice, and that can involve flame polishing when you're casting and some other different methods of avoiding oxygen being in the metal when it solidifies. So I think at that point, I'm sorry I've eaten into your time slightly, Kongtan, but one of our other speakers said, don't worry, we're going to be short, so you can take an extra minute. Okay. I'm not going to stand here. But.
No problem. Thanks a lot. Thanks a lot, Stewart.